Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of the early 19th century, the physics of invisible forces was a realm of profound mathematical elegance and deep philosophical unease, governed by the paradigm of instantaneous action at a distance, a legacy of Isaac Newton's gravitational theory. The forces of electricity and magnetism were understood through precise inverse square laws, the work of Charles Augustin de Coulomb, amplified by the powerful analytical machinery of Sima and Denis Poisson and Pierre-Simon Laplace, had erected a magnificent theoretical structure based on forces leaping across an empty, passive void. This was a physics of points, distances, and disembodied influence, a framework that was computationally powerful yet physically hollow. It is into this world of abstract mathematics and ethereal action that Michael Faraday, with his 1838 publication of the 11th series of experimental researches in electricity, introduced a radical and revolutionary materialism. Through meticulous and deceptively simple experiments, Faraday dismantled the idea of the passive void, replacing it with a dynamic, physically active medium. He gave substance to the space between charges, and in doing so, offered a new ontology for all of fundamental physics, initiating a conceptual lineage that flows directly through Maxwell and Einstein to the very heart of our modern understanding of reality. Faraday's intellectual journey was itself a departure from the established norms of European science. A man of humble origins, whose formal order ceased in his early teens, a bookbinder by trade and a scientist by sheer force of will and intellect. His laboratory was the Royal Institution, his mentor the great chemist Humphrey Davy, and his language was that of experiment and observation, a language he spoke with unparalleled fluency. This lack of formal mathematical training, which continental physicists viewed as a severe deficiency, was perhaps his greatest intellectual asset. Unfettered by the elegant but rigid formalism of potential theory, he was free to develop a mode of thinking rooted in physical intuition, in tangible processes, and in visualizable models. His earlier discoveries, particularly the landmark with 1831 demonstration of electromagnetic induction, had already sown the seeds of doubt regarding action at a distance. The appearance of a current in a wire from the mere motion of a magnet nearby suggested a process unfolding in the intervening space, a transient condition he termed the electrotonic state. The researches of 1838, however, represented a direct and focused assault on the orthodox view of electrostatics, a domain thought to be conclusively settled by Coulomb's law. Faraday sought to prove that the space between electrified bodies was the very seat of the action, an active participant in the phenomenon of induction. The 11th series of his researches, titled simply Non-Induction, is a masterpiece of experimental reasoning. The centerpiece of his investigation was an apparatus of beautiful simplicity and profound implication. It consisted of two concentric, spherical brass shells, carefully insulated from one another. The inner sphere could be charged with a known quantity of electricity, while the outer shell was connected to a sensitive torsion electrometer, allowing for precise measurement of any induced charge. His procedure began by charging the inner sphere and observing the equal and opposite charge induced on the inner surface of the outer sphere, a result consistent with existing theory. The revolutionary step came next. Faraday systematically filled the space between the two spheres with various insulating materials, or as he termed them, dielectrics. He tested air, and then replaced it with solid insulators like shellac, sulfur, and glass, according to the doctrine of action at a distance, where force acts directly between charged points. The nature of the intervening, non-conducting medium should be irrelevant. The force, and thus the induction, should remain utterly unchanged. Faraday's results utterly demolished this expectation. While the total amount of induced charge remained constant for a given initial charge, he discovered that the presence of a solid dielectric dramatically altered the interaction. He found that induction occurred through some materials with greater facility than through others. To quantify this effect, he introduced a new physical concept, specific inductive capacity, a numerical value representing a substance's intrinsic ability to support the propagation of electric influence. This is the quantity we now refer to as relative permittivity, or the dielectric constant. The discovery was a death blow to the classical model. If the insulating medium possessed a specific, measurable property that modulated the electric force, then that medium could be a passive void. The space between the charges was an active agent. Induction was an action transmitted by the contiguous particles of the medium, a chain of local polarizations propagating from one point to the next. He visualized this process through his powerful heuristic of lines of force, which he conceived as physical strains or tensions in the dielectric, originating on positive charges and terminating on negative ones. The geometry of these lines represented the direction and intensity of the force, and the space they inhabited was a field of physical stress. With this, Faraday replaced the ghostly action of the mathematicians with a tangible, mechanical, decidedly local. The reception of Faraday's work within the scientific community was deeply divided, a schism that traced the philosophical fault lines of the era. The continental school of mathematical physicists, steeped in the tradition of Laplace and Poisson, regarded Faraday's theories with skepticism, viewing them as qualitative, descriptive, and philosophically primitive. His lines of force seemed a regression to the mechanical ethos of the past, lacking the mathematical rigor and predictive power of potential theory. In Britain, however, his ideas found more fertile ground. The philosopher of science William Whewell, a significant influence at Cambridge, championed Faraday's work, recognizing its profound conceptual depth and its potential to reframe physical inquiry. The most crucial and consequential advocate was young William Thomson, the future Lord Kelvin. Thomson possessed the rare ability to see the deep physical truth in Faraday's vision, and the mathematical skill to begin its formalization. He demonstrated in 2845 that the equations governing the steady flow of heat in a solid were mathematically identical to the equations describing the distribution of electrostatic force in a dielectric medium. By mapping Faraday's lines of force onto the well-understood mathematics of heat flow, Thomson built a crucial bridge between Faraday's physical intuition and the abstract language of differential equations. This analogy gave the field concept a mathematical respectability it had previously lacked, making it palatable to a generation of physicists trained in the analytical tradition. One might observe with a certain dryness that it took the comfort of an existing mathematical structure for the community to fully appreciate a new physical reality. The ultimate vindication and glorification of Faraday's vision came at the hands of James Clerk Maxwell. Maxwell, a profound mathematical physicist, explicitly and repeatedly credited Faraday as the intellectual father of his own electromagnetic theory. He saw his own life's work as the translation of Faraday's physical ideas into a complete and consistent mathematical language. Where Faraday saw lines of force representing tension, Maxwell wrote down the equations for a vector field. Faraday's intuitive notion of an electrotonic state became the vector potential in Maxwell's formalism. The density of the lines of force became the divergence of the field, and their curvature and circulation became the curl. This process of translation culminated in the 1860s with the set of equations that now bear Maxwell's name. This unified theory of electricity and magnetism did more than represent Faraday's ideas, it extended them, revealing consequences even Faraday could have foreseen. The equations predicted that disturbances in the electromagnetic field would propagate outward as waves, and their calculated speed, derived from purely electrical and magnetic constants, was astonishingly close to the measured speed of light. This stunning result unified optics with electromagnetism and established the electromagnetic field, born from Faraday's dielectric medium, as a real, energy-carrying entity that exists independently of its source charges. The legacy of the 1838 researchers extends far beyond the triumph of Maxwell's theory. The concept of the field, which Faraday introduced as a physical entity pervading space, has become the foundational concept of all modern physics. When Albert Einstein sought to resolve the contradictions between Maxwellian electrodynamics and Newtonian mechanics, he did by promoting the field to an even more fundamental status. His special theory of relativity is built upon the principle of the constancy of the speed of light, a property of the electromagnetic field itself. His general theory of relativity describes gravity as the curvature of a space-time field. In the 20th century, quantum mechanics was merged with field theory to create quantum field theory, the framework that describes the fundamental particles and forces of the Standard Model. In this picture, particles themselves are excitations of their underlying quantum fields. The world is a cacophony of interacting fields. It is a testament to the depth of Faraday's insight that his portrait hung in Einstein's study, alongside those of Newton and Maxwell. He had provided the foundational ontology, the physical substance upon which the great mathematical syntheses of the modern age would be built. In conclusion, Michael Faraday's 1838 work on electrostatic induction was far more than a collection of clever experiments with brass spheres and shellac. It was a quiet and profound intellectual coup, executed in a laboratory instead of the salon. By demonstrating the active role of the dielectric medium, he methodically dismantled the centuries-old doctrine of action at a distance and substituted it with a revolutionary concept of the physical field. His genius lay in his unique ability to perceive the physical reality behind a phenomenon, a vision unclouded by adherence to a prevailing mathematical orthodoxy. He gave physics a new way to think about space, transforming it from a passive, empty container into an active, dynamic stage for the universe's fundamental interactions, others would provide the elegant mathematical scripts, but it was Faraday who first built the stage and illuminated it. The entire edifice of modern physics, from the radio waves connecting our world to the fundamental fields governing subatomic reality, rests upon the conceptual foundation laid by a self-taught scientist who dared to ask what was happening in the space between.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.